Good morning, everyone. It's time to start. I'm Nicola Surian from Italy, Padova University, and I'm going to chair the first session of the morning. So we will have, as you see from the program, two sessions dealing with disasters. So the first session will deal with the sediment supply and availability, especially we will see relation with landslides and debris flow. And so let's go to the first talk, which will be given by Lorenzo Marchi from National Research Council from Italy. So please, Lorenzo.
Thank you, Mr. Chairman. It's my pleasure to be here, and I wish to thank the organizing committee for inviting me in participating in the Gravel Bed River workshop. My talk deals with the linkage between instability phenomena, debris flows, and landslides with gravel bed river during floods. It's a complex and wide topic, and I will try to select. I've tried to select some topics with some issues that I think can be relevant both for the research needs and for the management, for the implication for hazards and risk management. And try to outline the problem. Basically, landslides and debris flow are responsible for sudden and spatially concentrated input to sediment to the channel network. This has several relevant consequences. For instance, channel aggradation is a quite obvious outcome of these processes. This favors channel widening and increases the probability of lateral instability, and this can also result into channel avulsion. But there is also another particularly relevant and dramatic outcome, that is the blockage of the receiving stream by landslide dams. These processes are not necessarily associated to floods in the receiving stream in gravel bed rivers. But when these processes do occur during floods, there are some particular aspects that deserve to be considered. Basically, the key is the fast evolution and the high intensity of all processes involved. The sediment transport during flood can be substantially increased by the input from landslides and debris flows. But if sediment inputs exceed the transport capacity, the channel instability takes place, and this occurs exactly during a flood. The inundation hazard is thus increased, and this can be an important process that could also undermine, make unreliable the estimation of flooding based only on water hydraulic modeling assessment. Regarding the possibility of channel or the blockage or the damming of the receiving stream, the high discharge during flood can reduce the likelihood of channel blockage, especially when the sediment inputs come from moderate debris flow or medium to small to medium landslide. But if damming does occur, in that case, the situation becomes particularly challenging because there is very high probability of a paroxysmal evolution. The landslide lake is filled very fast, and subsequent erosion and failure of the landslide dam can take place in a matter of a few minutes, hours. A very important issue are the space and time scales of the meteorological triggering events. In this case, we focus on floods and landslide triggered by rainfall, which is quite probably the most common process. I mean, convective cells, spatially limited in space and time, can cause shallow landslides, debris flows, but often don't produce major floods in main streams. It's a matter of the drainage basin area. Whereas longer rainstorms that involve a larger area and have a longer duration, typically mesoscale storm system, MCS in that figure, you see that plot of watershed area versus rainstorm duration. Well, in that case, both landslides, debris flows, and floods can take place. The problem in that case is not only the co-occurrence of different processes, but also the interplay, the overlapping of the flood response with instability process. And this emphasizes and enhances the possible impacts of individual processes. The remaining part of my presentation is basically split into two main sections. I will try to provide an overview, probably not exhaustive, but of the different types of interaction which encompass changes in the type of flow process. These will focus especially on the small upstream parts of gravel bed river, the increase in sediment transport, formation and collapse of landslide dams and the channel damming by debris flows, and also the topic of erosion and transport of large wood. Then we will have a short overview of the possible approaches to prediction. We will take into consideration both the temporal scale, rainfall threshold for landslides and debris flow, and the spatial scale. The answer to the question when this instability process could occur and which part where they could occur. Changes in type of flow process. In the steeper part, in the mountain sectors of gravel bed streams that drain steep catchments, a landslide can also change the type of flow process, triggering debris flow or hyper-concentrated flows in channels that are normally affected by floods with bed load. An example I would like to mention is this catchment in the Italian Alps. It was affected in November 1966 by change the type of process that started as an intense flood. It was a regional scale flood. It was part of it was caused by a rainstorm that affected most of northeastern Italy. But then several landslides occurred on the channel banks and on the slopes. There was some damming of the mainstream, and the failure, the sudden collapse of landslide dam, resulted in a high concentration flow that produced a large sediment deposition on the alluvial fan. Was it a real debris flow? Well, it has been classified as a debris flow, and me too, I share this interpretation. Actually, there are some clues, some description of the event that could support this idea. There are also some evidences, some other evidences that could suggest that it was not a fully developed debris flow. But anyway, what is important, in my opinion, to mention here is that something different from the initial process occurred due to the contribution to the interaction of landslides with this flood on this gravel bed channel. Another process, the increase of sediment transport, commonly often mentioned, commonly accepted, but seldom documented. And here, I apologize for repeating what has been presented also yesterday by Michael Attel, but Taiwan, after the Chichi earthquake and subsequent typhoons, became an ideal natural laboratory for studying these processes. The Chichi earthquake triggered many landslides, and then the typhoon Toroji, couple of years later, produced more and more landslides, and differently from the landslide caused by the earthquake, the ones triggered by the typhoon were larger in area and much more closely connected with the channel network. Well, the rating curves of suspended sediment shown a visible and strong increase of sediment concentration. And other studies which focused on channel aggradation confirmed this overall process of increase of increased sediment dynamics. We can move now to another important effect, channel damming and failure of landslide dams, again in Taiwan. The Shaolin landslide, which was studied in this paper by Feng, provide an excellent example of a sequence of events. A large landslide dammed the Shishan River, and the breaching of the dam due to erosion, overtopping of the dam, and erosion took place just 1 hour and a half after formation. And the resulting surge exceeded the peak discharge observed in the previous days when produced by the typhoon, the Morakot typhoon, indicating providing a good demonstration of the potential severity of this process. Again, this is interesting because it was monitored in a quite careful way. Another example, I think it's quite a well-known example because it's the Valpola landslide in Italy in July and August '87. But it provides it's possible in this case to present everything could actually occurred in that case. First of all, an intense regional scale flood with widespread landslides and debris flows. One of these debris flows caused the damming of the mainstream, which drains here an area of 500 square kilometers. The alluvial fan tube was then eroded, but a pond, some small lake remained upstream of this newly formed debris flow fan. Some 10 days later, a large rock avalanche blocked the valley and causing the formation of a landslide lake. also some casualties not directly caused by the landslide, but by the wave of muddy water in this weather. Fortunately, other villages had been evacuated just in time. 10 days later, a large landslide dam had a volume of 22 million of cubic meters when filled. Fortunately, the landslide dam didn't fail. There was also the flank of the valley that failed was forest covered, and there's also a picture of the large amount of logs transported by the landslide. Fortunately, the landslide dam didn't fail, but there was a difficult situation to manage because of the threat of landslide dam overtopping and failure. So some emergency control measures were taken. They involved quite obviously the landslide and dam monitoring, the installation of pumping station, but this needed some weeks to be implemented, this large pumping system. So there was a risk of landslide dam overtopping and failure, and it was decided to perform a controlled overtopping of landslide dam. There was several strong discussion about that because of the intrinsic risk of erosion and failure of the landslide dam. But this was studied on a physical model. The crest of the landslide dam was lowered by means of artificially lowered, and finally the controlled overtopping was performed successfully. And then in the following weeks and months, some more permanent remedial measures, which mostly consisted in the construction of 2 large bypass tunnels, were also implemented. Other processes that can cause channel damming are the progradation of debris flow fence. One example documented in the Italian Alps, the use of historical maps can help documenting these processes. It was possible using these historical maps, archive information, and other this kind of sources to see how the interplaying of debris flows and floods in the gravel bed river conditioned the evolution of this sector of the valley for over several centuries. Now, in the most recent decades, we know this because this catchment is now monitored for debris flow, for recording debris flows. In the most recent decades, debris flow magnitude was usually moderate, but due to the large amount of debris available, the possibility of much larger debris flow still exists. In another case, this time is in the French Alps, a careful collection of data on debris flow permitted also to evaluate the frequency of channel complete and or partial river blockage. Complete clogging, it was also possible to evaluate that must exceed approximately 20,000 cubic meters. More or less, the frequency of large or moderate debris flow remained almost constant in time, even if more careful collection of data in the most recent years and decades resulted in the collection of a number of debris flow that remained unperceived in the previous times. One more process that deserves to be mentioned is the erosion and transport of large wood. I've taken this picture from this paper. The first two authors are also attending this meeting. There are some comments about this process. On large landslide, also large volumes of wood can be eroded and transported to channel, but the role of large wood can be almost negligible because large masses of rock and debris make the wood volumes almost negligible. In this, for assessing these processes, a good approach is to implement a budget of large wood during floods. In the example, which is taken from this paper, the contribution from hill slope, that is basically from shallow landslide, was not so relatively moderate, lower than the erosion from the floodplain. But even in this case, it would have been sufficient to cause problems of bridge clogging. So the problem of large wood management is not only a matter of managing forest in the floodplain and in the river corridor. Also, the contribution of hill slope needs to be taken into account. The approaches to prediction, because I think I have some 10 minutes. Okay. Temporal scale. Will the rainfall that causes flood in gravel bed rivers trigger also landslide? And when this will occur? Typical question for people in an emergency room of a civil protection agency during a flood emergency in mountainous area. Spatial scale, how debris flow in tributaries will interact with the gravel bed river. Typical question that for people involved on watershed planning and implementation of design and implementation of torrent control works. Temporal prediction, probably the easiest tool, one of the most common tools. Critical threshold lines that identify minimum combination of cumulative rainfall or rainfall intensity versus duration. A number of these critical curves have been developed both at global scale and on particular regions. I don't think it's important to develop more of these critical threshold. One of the most important issues is increasing our capability of coping with their uncertainty, to provide reliable guidelines for determining how much we can trust on this critical threshold. And also, basically, traditionally, these data sets are based on rain gauges. In the past 2 or 3 decades, this was the main source of information. Now, the increased availability of the rainfall data, distributed rainfall data from weather radar could also provide an important contribution to this issue. Spatial prediction. Basic issue is the identification of catchment prone to debris flow, and with a basic separation between catchment affected by floods with bad load and suspended load, and floods with catchment potentially affected by debris flow. This kind of plot, this paper, also in this case we have one of the attendants of this workshop is one of the authors, is the most recent evolution of a series of studies that aim at discriminating debris flow catchment from so-called fluvial catchment based on morphometric parameters. The alluvial fan slope and an index of basin ruggedness, the Melton ruggedness index, the ratio of basin relief to the square root of drainage area. Of course, these morphometric conditions are not the only control. Also the availability, location, and location of sediment sources and their connection with the channel is important, but this can be a first tool for a preliminary discrimination of the catchment potentially affected by debris flow. We can move very fast to the models or equation for debris flow runout in inundation areas. I wish to mention amongst the most well-known and easily available equation, the empirical equation by Rickemann. Some simple models, this one by Iverson and colleagues, originally developed for layers, but then modified also for other types of debris flows. And I must run because it's almost finished. Also, this kind of models suitable for preliminary recognition of interaction between debris flows and the main streams and channel network. I would like also to mention another metric for sediment connectivity. No more a model for runout and for the assessment of inundation area by debris flow, but a tool that permits to determine the topographic control of on the linkage between different parts of a catchment with a target that can be represented by the receiving channel, the gravel bed river in the main valley floor. It's the ratio, these are the references, a ratio between an upslope component that takes into account drainage basin, the area upstream of a cell. This is done, the analysis is done on a raster, raster DTM, and the slope and the downstream component takes in account the distance from the target and also the slope. And there is also another parameter which relates to the impedance. It depends on vegetation cover, on the roughness of the surface, and so on. Pose an application to a gravel bed river in the Eastern Alps that this can provide. This I wish to stress that this is not a model for debris flow runout. It's a general portrait of the linkage between different parts of the catchment from the point of view of sediment delivery. If applied, it can also permit to ranking landslides and other sediment sources according to the likelihood of the sediment transfer to the receiving stream. It emphasizes the connection, the role of alluvial fans and other similar aspects. I think it's time to come to the concluding remarks. Basically, in order to cope with the link between landslides, debris flows, and floods in the mainstream, a number of approaches need to be implemented, which require skills on geology, hydrology, sedimentology, hydraulics, and these approaches do exist, but their proper integration is still a complex and challenging task. With particular focus on landslides and debris flow that occur during major floods, I would like to stress some topics that could deserve particular attention. The analysis of spatial and temporal scales of precipitation that can trigger landslides, debris flow, and floods, and especially in the possible combination of all these processes. The recognition of catchments susceptible to debris flow, not only in a static way, which can be done quite easily also now, but for specific rainfall events. And this will require combining morphological channel characteristics with runoff-related variables. The refinement in numerical model of the interaction between sediment pulses from debris flows and floods in the receiving stream, and also the modeling of recruitment and delivery of large wood. I have so finished my presentation, and I wish to thank you for your attention.
Thank you, Lorenzo. So, next speaker is Shenglun Shi from Chek Kung University in Taiwan.
Thank you, Chairman. Good morning, everybody. This is my name, Chen Lun Xie. I come from Taiwan, not Thailand, but Taiwan. And Taiwan is a very small island. Every time I say I come from Taiwan, or they say, oh, it's a beautiful country. I know Thailand. No, Taiwan. Here. And this is my outline. First of all, I would like to introduce some large-scale landslide in Taiwan. Then this kind of landslide, it caused some river process, some case study of riverbed process result from large-scale landslide. Then I would like to promote a countermeasure about such kind of extreme variation of riverbed process. In here, and the large-scale landslide means its area more than 10 hectares, or its volume more than 100,000 cubic meters, or its depth more than 10 meters. Here is Taiwan. Taiwan, unfortunately, there is a boundary of the Philippine Plate and Asian Plate. The boundary is on the island. So we got a lot of earthquake every year. And because the Taiwanese island, so they got a lot of typhoon. And you can see this is the typhoon track. During these 60 years in Taiwan here. So every year we got 3 times typhoon directly struck to Taiwan. From 1906 to 2000, averaged every year 3 times. But after 2000, it suddenly become 6 times. Maybe it's a climate change. About the climate change, it's really very severe rainfall. You can see every year, this is the cumulative rainfall. It's easy, more than 1,000 meters in a typhoon event. And its intensity per hour it's easy to over than 100 millimeter per hour. So such kind of heavy rainfall induce a lot of landslide and also cause a riverbed process. So about the climate change, I do some research in Taiwan. I want to grouping the climate change in Taiwan. This vertical axis is the rainfall intensity. The horizontal axis is the accumulative rainfall in a storm event. This is the situation now. If the climate change change into this direction, that means the accumulative rainfall less than 1,000 meters, but its intensity is more than 100 millimeters per hour. Then some shallow landslide debris for flooding will frequently occur. If change in this direction, that means the accumulative rainfall increased more than 1,000, but the intensity is not so bigger. And there will be some deep landslide or landslide dam occur frequently. But unfortunately, Taiwan is changing this direction. That means its accumulative rainfall more than 1,000 and intensity more than 100, so they got a compound disasters. All of disasters will occur in a very small area and in a typhoon event. This is the example, the landslide in a catchment before and after a typhoon. This typhoon Molak, in 3 days, its cumulative rainfall more than 3,000 meters in 3 days. And so you can see before this typhoon, the total landslide area is only 11,000, but after typhoon, it become 41,000. This is also it's a large-scale landslide example. Before the large landslide, it's a very beautiful community nearby the stream, and this slope valued. And you can see that. So the village completely destroyed by the large-scale landslide. And more than about 500 people were killed in this damage. After that, Taiwan government have do some field investigation. They want to find out how many potential LSL in Taiwan. After the investigation, we found almost 8,800 sites are the potential large landslide area. And within the 8,000 sites, they got 300 sites nearby the village. So it's very severe situation. And now I would like to introduce the riverbed process result from the large-scale landslide. We have a field investigation from 1984 till now, more than 30 years. Every year we do the survey in this basin. And this basin, its catchment is about 214 kilometers square, and river length about 38 meters. The landslide area in 1984 is about 1,300 hectares. And from that time, the landslide occurred. Then the channel river changed. At that time, you can see there is a very big landslide. And this is its sediment volume. And when the sediment moved to the main channel and it became a landslide dam, the deepest, highest part is about 60 meters, and its length about 200 meters. But now it become to the original situation. And this is the longitudinal profile during the 30 years. And the black one is the longitudinal profile in 1981. Then the dashed line is in 1984. So you can see here they got 60 meters in depth. But very interesting, when the sediment moved to the upstream of a notch, the notch means a very narrow curve section. And it almost stopped here. So from 1981 to 1984, here the maximum riverbed aggregation is almost 60 meters. But from the notch to here, they got a Savo dam, it's only 8 meters. From 6 meters to 8 meters. In the downstream of the Savo dam, it's almost 3 meters. But after, from 1984 till now, it's back to the original riverbed. And here, still plus minus 5 meters. So you can find very interesting things. That means the natural notch, it has a function of sediment control function very similar to a Savo dam. It can control the sediment here. And this is its photo. And the landslide occur here, and the natural dam occur here, and the red line, red point is a notch, and here is a Savo dam. And this is a mountain. We call it coastal mountain area, and this is central mountain area, and this is valley. And this valley is the boundary of two plates. The one is Asian plate, another one is Philippine plate. So they got a lot of earthquake and landslide in this area. But now I would like to introduce this 5 segment. It's riverbed variation. The vertical axis is the sediment material amount, and the horizontal axis is the time. From 1984, that is the time of the landslide occurred, until now. And you can see the upstream segment, S1, S2, and S3. At that time, it increased rapidly, then it gradually decreased. Till now, it almost in equilibrium. But in the downstream, when the upstream riverbed erosion, then the downstream become aggregation. But till now, it still have some deposition, and the riverbed is in high situation. Its particle size variation in the upstream, you can see it when the riverbed deposition and it become finer. When riverbed erosion, then it become closer. in upstream. But in downstream, this process have some time lag with the upstream one. Okay. The closer D90, they have also such tendency. The another case study is called Taimari River. From 2009 till now, this river basin is more than 200 kilometers squares, and it have a large-scale landslide, about 800 hectares. And this landslide, only this landslide, its area is about 280 hectares. This is before landslide, and you can see here. After only one typhoon, you can see a lot of landslide. And this landslide, soil block moved to the main channel and become a lake, and this is the landslide dam. And you can see the photo. This is a lake, and there's the landslide. And I also separate into 5 segments to explain to you. In this 5 segment, this is also its longitudinal profile. And the blue one is before the landslide. And the black one is in now situation. And you also can find here got a notch, a very narrow section. And the landslide soil block moved here and controlled it by this notch. And in downstream of the notch, the riverbed variation is in very small ranges, but in the upstream, it's quite severe. And except the notch, we also found a very interesting phenomenon, that is rotation riverbed variation. And you can see the landslide dam eroded. So in this section, you can see in the upstream of this section, it eroded. In the downstream, it deposition. But in here, it on contrary. The riverbed like rotated. You can see also the notch here, a very narrow cross section. Okay. In case of Taiwan, we have a lot of earthquake, typhoons, so also induce a lot of sediment-related disasters, such like I introduced to you. So my government, they want me to provide a countermeasure for the such kind of sediment-related disasters. From 6 years ago, we started a project called River Basin Sediment Management. River Basin Sediment Management. Its motivation is in 2006, our government will have a new Ministry of Environmental and Resource will be established. And this ministry integrates the Water Resource Agency, Forest Bureau, Soil and Water Conservation, Geological Survey. They integrate together. And this is the motivation of River Basin Sediment in Taiwan. Actually, in Taiwan, the Forest Bureau lay in charge of the upstream, Soil and Water Conservation Bureau lay in charge of the middle stream, and the Water Resource Agency lay in charge of the downstream. But now they become one ministry. So the purpose of the sediment management at river basin scale, the purpose one is to mitigation of sediment-related disaster. The purpose two is to stabilization of riverbed over the coastline. About the conception of the SMRB, they got two cases, one from China, one from Japan. In China, I call it is a centralized management, because it have a very big reservoir for the sediment control. The case study is the Yellow River sediment control plant in Yellow River. The another one is if the mention haven't the big enough reservoir for sediment control, then you can control the tributary sediment run out in order to control the main channel riverbed variation, such as the case in Japan, Abekawa. And they do some tributary sediment control in order to control the main channel riverbed process. And this is the case of Yellow River. And this line is the main channel. And after here, it's the downstream of the Yellow River. And they use this 4 reservoir to control the downstream riverbed variation. And they found if the sediment runoff, sediment transport rate, and discharge and the proportion of fine particle satisfied by this formula, then the downstream riverbed will be unstable. So they use these 4 reservoirs to satisfy, to control the discharge and proportion and sediment transport rate. The another case in Japan, I call tributed management. In Abekawa, there is no big enough dam, so they use some tributary sediment control in order to stabilize the main channel. In Taiwan, we have such kind of frameworks. The first of all, problem analysis, then to make a plan, and then we use some model to do the analysis and evaluation, and there is a goal set there, and this is the framework of SMRB. About the goal, the SMRB, I provide an allowance variation range of riverbed, allowance variation range AVR. That means you can see they got 4 lines. The top line is the elevation of bank crown. The bottom line is the elevation of bank base. And here got 2 dashed line is the range of the allowance variation range. And you can see the maximum of this line are installed as a drain of design for safely. And its minimum is to prevent the foundation damage of a dike. In coast, of course, you can install the maximum AVR to prevent the block of river mouth and harbor. And in the minimum, you can install as to prevent the foundation damage of sea dike. But problem is how much money do you want to spend and how much time you want to take the risk. And this is the AVR, maximum of AVR, minimum of AVR. And the snake line is the riverbed. And after a large scale landslide occurred, and maybe your riverbed elevation is here or here. So how much time you want to go into the AVR? And it concerns about your cost and, of course, the risk. So if you take a very long time, then the cost will be very low. You didn't need to spend such a lot of money, but on the contrary, your loss will be higher. So you can use this line to make a decision, optimize time. That means TEO, it is optimized time. You can control the riverbed variation, go into the allowance variance. But you need some tool to do the analysis. We use the three basing. The one is prototype. We do the monitoring in the field. And you need a numerical model of river basin. This is another river basin. And the third one is physical model. We use these three: monitoring, numerical, and hydraulic model. And this is our monitoring. We choose a segment to control its mentioned riverbed process by some rainfall gauge, velocity, and concentration, and bed load transport rate, and some water elevation. Use such kind of monitoring to understand the characteristic of the basin and the mention. 5 minutes, okay. And of course, we have a numerical modeling. First of all is watershed model, from the rainfall to its surface runoff and sediment yield. And we have a river model, a modular bed river model, to simulate the river flow, river bed variation, and sediment transport. But in here, I would like to emphasize that is, in Taiwan, they got a lot of notch, very narrow cross section everywhere. So in our equation, we need to modify the latent pressure effect here. Otherwise, the flow simulation were not so reasonable. And also, we have a coastal model we call one-line model to simulate the longshore current, longshore drift, and coastal variation, the conservation equation and the drift equation. Except the numerical model, we need a very good quality database. From 1996 to 2013, about 8 years, in my university, we do the whole island investigation to establish such kind of database. So this database have the accumulated rainfall with a landslide area. The relation with the area to volume, the map of soil erosion index, the rating curve. Of course, we have a lot of multi-lidar talent data. That is the topography data. Every 2 years, we have a whole island lidar data from 1996 to 2013. We also have to do some hydraulic model test. And this is the case study. We use a reservoir basin to predict and to simulate the sediment budget from its sediment yield to sediment output from the tributary to the main channel. And finally, go into the reservoir so we can understand our simulation result is reasonable or unreasonable. And this is our website. In every basin in Taiwan, you can find out 3 data. The one is its sediment yield. The another one is how many sediment remain in the slope and how many the sediment go into the main channel. And such kind of database is well established in Taiwan. Okay, about the conclusion. The large-scale landslide occur frequently in recent years and induce a long-term wide impact on riverbed process. Such terrific variation of riverbed result from LSL is a big challenge to river engineering. And sediment management at river basin scale are provided as a new conceptual countermeasure for those challenges. In the sediment management plan, we install AVR, that means allowance variation range, as a goal. And we use prototype monitoring and the numerical model and the physical model to do the sediment management at river basin. Thank you. Thank you so much.
Well, it's time for questions, so both the speakers can stay up for the questions. Okay.
Professor Shea, your river basin management model is very ambitious. I'm impressed.
Thank you so much.
And I'm curious, you listed things that are associated with landslides. At the end, you said cumulative rainfall.
Yes.
And correlations of area and volume and this sort of things. Do you actually have in this model a plan to take a precipitation forecast and predict the amount of sediment influx from landsliding? And if so, how do you plan to do that?
You mean the precipitation prediction?
Prediction, yeah.
No, I haven't do the rainfall prediction.
Is that a goal of the model, though? Is that what you intend to do? Or I just saw an association, but I wasn't quite sure how you connected that to sediment.
Yes, yes. It's really a very big problem. If you don't know the rainfall in the future, and how can you simulate sediment yield in the future? But we didn't use the rainfall prediction, but we use a historical data to do some static analysis, and using such kind of rainfall repeated. We don't use a unsteady rainfall, but we concern about the steady rainfall. Use such historical analysis to get the rainfall scenario. We haven't to predict the rainfall in the future.
And in that analysis, I'll be done, sorry. What's the relative importance of your large landslides to the many, many shallow, small landslides you have to sediment?
Yes, yes. As my presentation, Taiwan, the accumulative rainfall more than 1,000, and its intensity also more than 100. So the compound disaster occurred everywhere. The compound disaster means the shallow landslide, deep-seated landslide, flood, debris flow, and landslide dam, and it's dam break. So actually, in my sediment management plan, we concern about the sediment yield, not only from the deep-seated landslide, but also include the surface erosion or shallow landslide. We combine them together by the rainfall and the landslide volume relationship from the historical data.
Gordon Grant?
Gordon Grant. Thank you both for a very interesting set of presentations. This is one of these terrible statements masquerading as a question, but at the end of it there will be a question that's really directed at both of you. It is my impression that if you look at the overall field of landslide prediction, particularly landslide dam prediction, that we have many good case studies of individual events, and you've both given us really nice examples of some rather dramatic events. But we have a little bit of effort to develop either empirical or theoretical models that allow us to really predict where these landslides are going to occur. Because, and you both talked to that as well. In both cases, I think speaking largely about rainfall-triggered landslides and how do we put rainfall intensity and magnitude and duration predictions into the landscape. But it seems to me that given the scale of the problem, and also given the fact that rainfall is not the only triggering event, we also have seismically triggered landslides as well, that we're still rather at an immature stage in terms of being able to predict where these large landslide dams are likely to occur. And so here comes the question. That was the statement. Here comes the question. The question is, what is your sense of what the state of the art is in terms of being able to speak more broadly in a predictive way about where landslide dams are likely to occur and also where they're likely to persist long enough to cause these secondary cascading series? What is your sense of where we stand with all that?
I would like to explain the large scale landslide in my presentation. It's an individual study, so we can have a more detailed data and to do some stable analysis, such kind of that. But in the other way, in the sediment management at river basin, in that topic, we didn't use such kind of physical model to do the predict. But we use the historical data from the field. We make a static from the rainfall, accumulative rainfall, and the landslide volume. We only use such kind of data to do the sediment management plan. Okay.
Thank you for the comment and the interesting question. I think that yes, this is an important issue. I think the possible answer is we could distinguish the situation of existing large-scale landslides that have been observed. The location is known, and even if these landslides have the activity is relatively slow-moving, moderate, these large-scale landslides have to be kept under observation, monitored, and possible paroxysmal evolution has to be modeled. This is being done in the European Alps for several landslides. So the first answer but this is the easiest situation. We do know that there are some landslides, and we must pay attention to their evolution. The situation becomes much more difficult when dealing with potential landslide sites. So this is a typical issue for geomorphologists and engineer geologists. I think that some inventories of deep-seated gravitational deformation can be useful because they could help identifying situation, parts of valley flanks or hill slopes that could evolve into a large-scale landslide. Another way is to consider the geostructural settings, geomorphological setting of large-scale landslides that have occurred in the past, and this can help recognizing also other sectors of parts of valleys or valley flanks that have similar setting. There is some work has been done also on this direction, and there is still room for further development for improving this the recognition of sites suitable to large-scale landsliding.
Philippe Belludi, University of Grenoble. First, I want to greet the scientific committee to couple such, for this choice of presentation, the way they are coupled, and every session is like that. I have a small question, a remark about the pertinence of discharge sediment load rating curve in these sort of events, because everything comes from upstream. But the question is about the assessment of the hazard in such basin. And Lorenzo spoke a little bit about this at the end. You have, usually we have assessment of the flood hazard by predetermination of events. And in some cases, in some basin, in some events, we have additional hazards due to sediment load, which is produced by landslides or something else upstream. Do you think that, what is your opinion about the common practice of managers of rivers? Is it something we have to integrate, especially for small basins, sorry? Do we have to integrate this in the hazard predetermination, sorry? Or is it something we have to put above as an additional hazard for certain basin? You told it. For certain hazard as an additional hazard. It was clear. And is it really done, actually?
A first step could be to include try to combine the two effects. I think it will be possible to do this working on the basis of scenarios. Which will require some flexibility. I mean, for instance, the flood hazard mapping without sediment input, or assuming that sediment input from landslides or debris flow occurs, and then a different modeling. This will be a way to cope this problem. It's easy to discuss about that here. It will be much more difficult to transform this into practices to be implemented in hazard plans, because, of course.
In Taiwan's case, the disaster, they are not individual, they are not independent, but they combine together. I call compound disaster. So in every case, you need to integrate the rainfall, discharge, sediment, then slide. You should to integrate all phenomena together. But problem is your analysis to quite enough? That is need the academic research to do more, to do their best.
Yeah, my question is for Professor Shi about some of your case studies. There's been quite a lot of work done on dispersion and translation of landslide deposits once they get into river channels.
Yes.
And it seemed to me, looking at your slides, that the sediment pulse, or the landslide deposits seem to translate until they hit the channel constriction, and it's almost like there's then a forced dispersion of the material. I wonder whether you've thought about it in that context, whether you're doing any work on that in that context?
Can you repeat your question once time again?
Sure. So there's been some work on, so once the sediment gets into the channel
Yes.
from the landslide, it moves then downstream by translating in
Yes.
some cases, and by dispersing in other cases, right?
Yes.
So the amplitude of the wave just declines. And there's been, the literature seems to indicate that dispersion is really what dominates in terms of movement of those waves. And I just wonder, your slides seem to indicate that there was a translation until it hit the notch, and at the notch it started dispersing. And I wonder whether you've thought about that
Yes,
problem.
actually, about the sediment control function of the notch, I have do some study from the experimental study to the simulation study, and I found when the river-wise from a Dutch-wise to a very narrow section, if the ratio more than 3, I mean the largest one to the narrowest one, the ratio more than 3, then the sediment control function will be very, very good. But when the ratio up to the 6 or 8, it almost is stable, no more function than that. So I found the ratio from 3 to 7, it will be very, very good sediment control function. But why? What kind of hydraulic mechanism of the notch? That is the, we called choke. You know choke? When the supercritical flow flowing in the downstream, and when it go into the notch, then it have a phenomenon we call choke. From supercritical to subcritical, there is a hydraulic jump occurred. And in the area of hydraulic jump, the sediment will deposit there. Okay.
Thank you. Mike Miles from Canada. In 2013, we had a very sizable flood, and hyper-concentrated flow deposits in the mountains caused a lot of damage on alluvial fans. Dr. Matthias Jacob has looked very carefully at the magnitude, frequency of historic events, and the likely risk of fatality. On this basis, he has recommended that future mitigation works be designed for the 1,500 to 3,000 year return period event. I would be interested in what kind of design criteria or acceptable level of risk you have found in your studies.
You mean the risk?
What I'm interested in is what level of risk is acceptable in Taiwan or in Italy or Europe?
Okay. About the disaster risk assessment, actually we have done a lot of for every basin. In the past time, we do the risk assessment only individual disasters. For example, the flooding, inundation risk, or the earthquake risk assessment. We separate to consider such kind of risk. But if you want me to say what kind of risk level we can accept, in the earthquake, we can allowance the building half destroyed it, but not completely collapsed. Such kind of that, or some lifeline can be in a normal function, such kind that. This is the what kind of risk that we can allowance. But now we want to integrate all of the disaster together and to consider about the system risk assessment. But I cannot very good to answer to you what kind of level. Maybe when I have a good answer, I will mail to you. But now it is hard to answer for me.
Hazard and risk mapping in Italy is based on 4 classes within the 2 higher classes corresponding to strong limitation to land use and to building. For flood risk, it's associated to different return period. It seems to me it's 300 and 100 years and 30 years for the more frequent floods. For landslides is based the evaluation is based on a Boval decision matrix that takes into account also for floods the flow velocity and flow depth. And in the case of landslides, the analysis is based mostly based on historical on data from historical archives.
James?
James Bathurst, Newcastle University. I have a question probably for Lorenzo, but possibly other people in the audience, concerning the role of vegetation and how it may affect debris flows from shallow landslides. You've rightly said that you can have a landslide, but whether the material gets into the river, of course, depends upon the connectivity. At Newcastle, we have a catchment scale landslide sediment yield model, which you've kindly referenced in your paper. When we set it up, we were forced to use a kind of rule-based approach, partly because we didn't have other information, on the development of debris flows for transferring the sediment from the shallow landslide down to the river. And for grassland catchment, we assumed that shallow landslides would be relatively weak and would not transform into debris flows and would therefore just stop on the slope. In the forest, of course, you don't get so many shallow landslides because of the strength of the tree roots, but when they do occur, we had to assume that they were very strong ones because they'd broken the tree roots, and that therefore there would be a debris flow that would carry the material all down to the bottom of the slope. Now, this was something of an assumption, and I'd be interested to know whether you or anyone in the audience can confirm that this actually happens with forests, that if you do get a debris flow in the forest, it will carry on down to the bottom, or whether in fact we need to take some other approach.
Thank you for suggestion and for regarding the observation. Yes, most debris flows in the Alps originates above the timberline, but the debris flow also affect forested slopes, and they are quite effective in transferring trees and logs to the debris flow channel. Then, depending on the width of the debris flow channel, further downstream transfer can occur or can be prevented by if the debris flow channel is very narrow. The trees and logs could also deposit in upstream reaches. In other cases, debris flow are very effective conveyors, and I agree when hills, an instability, shallow landslide affects forest slopes, they can deliver quite effectively the trees, all the vegetation.
Thank you.
Yeah, you.
Okay, thank you. I'm Egashira, the International Center for the Water Hazard and Risk Management Center, the Public Research Institute. The Professor Shah, I think it is very valuable for you to introduce the allowable riverbed variation in river management. By the way, you showed the impact of the sediment supply on the river morphology in two rivers.
Yes.
One is how to say?
Shofeng River.
Yes. Shofeng River, and
Another one is Taimali River.
Tamali.
Tamali.
I think it is interesting. In the Shofeng River case, the river longitudinal profile approaches in the original shape.
Yes. Yes.
On the other hand, that river approaches maybe different from the original. Your data may show such tendency.
Yes, in Shofeng River, in this case, from 1984, they got a big landslide occurrence. Then the riverbed aggregation, about 60 meters. Then after 30 years, in the upstream, the riverbed back to the original riverbed, but in downstream is still in a deposition process, even 30 years.
Yeah, so when we consider the allowable riverbed variation,
yes,
such the catastrophic change of the final stage,
yes,
may take place.
Yes.
Such phenomena should be predicted in river management. I'm thinking about that.
Okay. About the river management, we need to do some control. And people like to control, and some people dislike to be controlled. And in my opinions, if we want to make the disaster mitigation or the ecological in a very good condition, the control is necessary. And in my opinion, in the viewpoint of disaster mitigation, I provide a allowance variation range of the riverbed. But in other case, in the ecosystem, if you want to control it, you also can have a a allowance variation of, for example, discharge, temperature, or sediment size or sediment transport rate to make such kind of allowance variation. And it will be very good for the ecosystem. And if you want to combine the disaster mitigation and ecosystem together, and you need to consider more allowance variation index.
Okay, we have time for the last question.
Thank you. Kimberly Hill, University of Minnesota. I had a question for Lorenzo. Debris flows, hyperconcentrated floods both came up. Debris floods didn't, but I'm wondering if you can give a sort of quick distinction between the three and describe how it's helpful in predicting and mitigating hazards. Yeah.
The differentiation between debris flows
and hyperconcentrated flows, and how if it is helpful, maybe it's not helpful in predicting hazards, but if it is, how is it helpful, and how does one distinguish between the different
as you know,
potential?
there are several classifications that often don't agree. For some authors, don't use, especially in Europe, the term hyperconcentrated flow, and sometimes the debris flood is preferred, but is not exactly synonymous. Actually, we have all the spectrum, all the range of processes to take into account. In my experience, sometimes the fully developed debris flow are observed, and the hyperconcentrated flow, well, is not limited to high intensity events. Hyperconcentrated flow can be, it seems to me, also a low flow with high concentration. When coping with a flood situation, it's not easy to predict when dealing with when focusing on prediction. If a debris flow has if a catchment has the potential for debris flow, that process should be the target.
So was your choice, I mean, you focused on debris flows, though, and not any of the others. Was that intentional, or was it just to use one word and...
When, for planning purposes, I think that the most severe process has to be taken into account. When for an ex-post analysis, for a post-event analysis, there is possibility of a finer recognition based on the features of the deposit and so on.
Okay, thanks to all. And thanks again to the two speakers. We have to stop here the discussion, so thanks. So it's time for a coffee break.